Batteries. Those heavy little cylinders or bricks are now a ubiquitous source of power for our modern lives. But how do they actually work? Batteries have a positive and negative terminal, and if we connect those, electrons will flow from the negative to the positive side. We call this flow of electrons current. The difference in electrical charge between the sides of the battery is called a potential, which is measured in voltage. This potential is the voltage that batteries are named after. If we have something in between, we can use that flow to do work, like lighting a light bulb or powering your cell phone. The energy traveling from the negative to the positive terminal is a lot like a snowboarder going downhill. If you let it, it'll slide all the way to the bottom. But if you put something in its way, it can do pretty cool things. Just like someone on top of a hill can't directly teleport to the bottom of the hill, electrons can't just jump through space. Usually. In order to bridge the gap, conductive wire like copper or other metals is needed to make their journey easier. This ability to route electricity is what allows us to harness it. But other substances besides wires are able to conduct electricity too. We've all heard that you shouldn't be in or around water in a lightning storm. This is because ionic solutions in water are able to conduct electrons. But what's an ionic solution? Well, water on its own isn't conductive, but water in nature or in your tap is almost never pure because there are small amounts of dissolved minerals and chemicals present. The water in your sink has likely been treated and often contains fluoride ions, which are good for your teeth. For those who have tried well water or spring water that hasn't been treated, there are other ions naturally present in the groundwater, such as calcium carbonate. There are also likely dissolved salts, like sodium chloride, which we know is table salt. This and other salts are present in high concentrations, especially in the ocean, which is why it's salty. Regardless of their source or what they are, many of these compounds will dissolve in water into their ions, which are positively and negatively charged. The water molecules help to stabilize these ions and prevent them from recombining. Now we're in business for conduction. Instead of electrons moving through the solution, the ions are able to move to balance the difference in charges. If the positive and negatively charged wires coming from our batteries are both in solution, the ion moves to balance the charges and a current flows. But even ions have their limits. If the potential across the two terminals is great enough, we can cause chemical changes in the ions. These chemical reactions occur on the wires we place in solution, which are collectively called electrodes. The two main reactions that occur are called oxidation and reduction events, or redox reactions for short. Oxidation is the loss of electrons, which occurs at the anode. Reduction is the gain of electrons, and it occurs at the cathode. An easy mnemonic device to remember these is oil rig, which stands for oxidation is loss and reduction is gain. Here's a real example. If we start with zinc 0 and copper 2+, we will end up with zinc 2+ and copper 0. To break this down and see the actual reactions that occur in solution, we can look at the redox half reactions, which separate the oxidation and reduction events in a given reaction. Here we can see zinc 0 goes to zinc 2+ and 2 electrons, so each zinc atom loses 2 electrons to get a charge of +2 and is therefore oxidized. Copper 2, on the other hand, goes to copper 0 by gaining 2 electrons to become neutral and is therefore reduced. Now let's turn to a subsection of redox chemistry called electrolysis. The word electrolysis comes from electro and lysis, which are Greek roots. Fun fact, electro as a prefix comes from the word electrum, which means amber. Amber is a natural resin that produces static electricity when rubbed. Lysis means to unbind or break. This is appropriate because electrolysis involves the breaking of chemical bonds using electrical energy. Electrolysis works by applying a large potential between our electrodes. By applying this large potential, we can drive the oxidation and reduction of certain species in solution, which leads to the breaking of chemical bonds. Today, we're going to be doing an experiment that does just that, by connecting a 9-volt battery to an electrolyte. Hopefully, we can perform some electrolysis. Now ideally, we could choose the exact species that undergoes redox chemistry at the electrodes. That being said, chemical systems are complicated, so let's take a look at some of the half reactions that might occur in our system. Firstly, let's look at our desired half reactions. nitrogen gas plus 6 electrons and 6 protons, giving us 2 equivalents of ammonia, which is a reduction of nitrogen. And secondly, 3 equivalents of water becoming 1.5 oxygen molecules, 6 electrons, and 6 protons. Next, let's take a look at another possible reaction, the electrolytic cleavage of water, with the half reactions as follows. 2 water molecules gain 2 electrons and release hydrogen gas, as well as 2 equivalents of hydroxyl anion. This is a reduction of hydrogen. Water also loses 4 electrons and 4 protons and releases oxygen gas. This is an oxidation of oxygen. From the nitrogen introduction video, you'll know that breaking the N-N triple bond in nitrogen gas is really tough, but maybe 9 volts is just the thing we need to do it. This is the reaction that we're going to be performing with you, so I'll see you guys in the following video on how to set up your electrolytic cell and how to run the experiment.